Many of you would have heard of the term called gravitational lensing, but what is it? Let's dive deep in to understand what this phenomenon is. As you may know, light travels in straight lines, but when it passes near a massive object such as a galaxy or a black hole, its path is bent by the gravitational force of that object. This bending of light can cause the object to act like a lens, magnifying or distorting the image of a background object, allowing us to see objects that would otherwise be impossible to detect. One of the most famous examples of gravitational lensing can be seen in the Hubble Space Telescope's images of galaxy clusters. These clusters are so massive that their gravitational fields can bend and distort the light of more distant galaxies behind them, resulting in breathtaking and unique images of the cosmos. But gravitational lensing is not just about pretty pictures. It has important implications for our understanding of the universe, and it's a topic that continues to yield new discoveries and insights. For example, by studying the effects of gravitational lensing, we can learn about the distribution of matter in the universe, the nature of dark matter, and even the existence of exoplanets. Gravitational lensing comes in two forms: strong and weak. Strong gravitational lensing occurs when the foreground object is very massive and the background object is perfectly aligned behind it. This can result in a highly distorted and magnified image of the background object, which can appear as a series of bright arcs or multiple images. The most famous example of strong gravitational lensing is the Einstein cross, which consists of 4 images of a single quasar arranged in a cross-like shape around a foreground galaxy. Weak gravitational lensing, on the other hand, occurs when the foreground object is less massive and the background object is not perfectly aligned behind it. This results in a subtle distortion of the background object, which can only be detected through statistical analysis of large numbers of objects. Weak gravitational lensing has been used to measure the distribution of dark matter in the universe and has provided important clues about the nature of dark energy. The amount of gravitational lensing depends on several factors, including the mass and distance of the lensing object and the distance of the background object. One of the most exciting recent developments in gravitational lensing has been the use of machine learning techniques to analyze large datasets. By training neural networks to recognize the subtle distortions caused by weak gravitational lensing, astronomers can now detect and analyze lensing effects in unprecedented detail. This has led to new insights into the distribution of dark matter in the universe and has the potential to revolutionize our understanding of cosmology. But gravitational lensing isn't just about cosmology and astrophysics, it also has practical applications here on Earth. For example, the technology used to detect exoplanets using microlensing can also be used to detect small asteroids and other objects in our own solar system that could potentially collide with Earth. By monitoring the brightness of distant stars over time, scientists can detect the tiny changes caused by the gravitational lensing effect of a passing object and use this information to determine its mass and distance. One other use of gravitational lensing is to study the structure and evolution of galaxies. By analyzing the distortions in the light of distant galaxies caused by the gravitational lensing effect of foreground objects, astronomers can map out the distribution of matter within the galaxies and study their formation and evolution. Gravitational lensing is truly an incredible phenomenon based on the theory of general relativity by the great scientist Albert Einstein. I hope you found this video informative. Subscribe for more awesome content in the future. Thank you.